Hello everyone, welcome to a new lecture in our computer vision course. So I know for now that we are working with 1 week on, 1 week off. Last week was off, previous was on, this week is on, next week is off. So 1 week yes, 1 week no. So we have a pattern like this. But hopefully after that we will have the lecture in regular schedule. Okay, but I told you from the beginning, one of the drawbacks of having lectures on Monday, that in the spring we have lots of Monday breaks. Okay, but this will be recovered by some recorded lecture. So I will post some recorded lecture for you to watch on your convenience time. Okay, so getting back for what we start in the previous lecture, we stated that our goal right now, after we start to understand the image and learn how can we extract some information from the image that we learned so far, which are the edges, we want to use this information one way or another to understand or extract the objects inside the image, or do it for other tasks like image matching or panorama generation or any of those type of applications. And to understand or to start to work on that, we said that we will work with this sequence. What is this sequence? We said that we will first look to detect key points or points of interest in our images. And for the description of the key points or the points of interest, we said that there are two schools in that. One school stated that corners considered to be one of the important points in the image, and around the corner there are lots of information that we can use to understand and describe the image. Another group said that there are information with the blobs, and the area of the blobs has lots of information that we can use also to understand the image. So those are the two schools within this track. But in both cases, we will start to extract points of interest. Whatever those points of interest are, can be corners, can be blobs. Second step is to extract features around those points of interest. So if the points of interest are in the corner, in this case, I need to understand the area around it. So the point itself is important just to know the surround area. Okay? So I can't use the point by itself. I need the area around it. How I can describe this area? I will generate feature vector. Vector that has some kind of information around this area. But this feature vector will be the same in case of the corner or the blob. The answer is no. If we are working with corners, we have something. If we are working with the blobs, we have another thing. Okay? But in all cases, we are extracting vector, and this vector has some numbers. Those what we will call feature vector. After that, we can do whatever the task we are looking for. If we are looking for some object, we will compare that feature for the object with the feature that we extract from the image to search for the object. We are looking for panorama view, then we will extract the feature from each image and we will try to do stitching over this. If we are looking for 3D view, we can make the match and do 3D extraction from the 2D, from the left and right image. Okay, so it doesn't matter what exactly the task that we want to do, it will end up that we will follow these 3 steps: detect points of interest, calculate the features around those points of interest, then do matching between those features. We started last time by understanding the first type of feature, which are the corners. We said that those features must be unusual. What was the meaning of unusual word that we described? We said that it needs to have maximum change in view. Meaning, if I was in some place and make a movement in some direction in the image, I need to see something else. So here, if I stand or stay in this point, then I shift this window in any of those directions. Will I see anything new? The answer is no. I will see the same exact view. Okay? So, gray color, move this direction, gray color, gray color, gray color, gray color, everywhere. So, nothing new. That's why we will call this area flat area. It doesn't have anything to interest for me. How about if we are at this point? Now, if you try to move up or down, will you see any change? Shift it up, shift it down. No. Almost the same value, right? So no change in this direction. How about if you move in the other direction? You will see change or no? Yes, this line position will shift. So if you subtract this from this, the value will not be 0. Here, if you subtract this from this, the shifted window from the original window, the difference will be absolute 0. They are typical, they are the same. Here, if you try to make this shift in this direction, the difference is 0. If you do it horizontally, the difference will not be 0. But it will not be that big. Yes, it's not 0, but it's not that big, plus 0. How about if you are at this exact point and you do shift in any direction you'd like? This direction, this direction, this direction, anyway. You will find that the difference between both of them is large. Okay? So that's exactly the meaning of the unusual. Something that has maximum change in the image. If you look to all those 3 points, you will see that this is what we call the flat area. Flat means flat, no information. Nothing that I can use to compare my data. As an example for this, if you are driving car in the desert, will you see anything except the sand? Can you use the camera there to find your path? Sand, yellow everywhere. So nothing to extract from there. Okay? So in this case, flat area will have no information for you. How about if you have change in one direction but not the other? In this case, we are saying that we have edge. In this direction, we have change. In this direction, we don't have any change. So what we have here is an edge. On the other hand, if you have changes in any direction, in this case, you will have corner. And if you have a corner, you have an unusual point we need to catch. Now, mathematically speaking, how can we extract this process or find the corner? We said we will do exactly the same steps that we described. So I will start by a random window. I will call it I of x and y for any value of x and y, any value of your choice, it doesn't matter. Okay, so this point is x and y. Now I will shift this window with a value u and v. The shift in the x direction will be u, the shift in the y direction is v. Remember, where is my origin? Here. This is the x axis, and this is the y axis. So this shift or this change in the positive direction of the x and positive direction of the y, not in the negative. Okay? So this point is nothing but x plus u and y plus u. And the new window that I have in this place, it will be I of x plus u, u plus y plus v. Now, what we said is, I want to subtract the newer position from the older one. So the newer position is I of x plus u, y plus v. Then I will subtract it from the older one, which is I of x and y. Very straightforward. I will square it. Why will square it? Why do we need to square that? What is this?
So difference could be negative.
Okay. Do we care about the negative? We don't care about negative value, but we want to measure the difference. Is it positive? Is it negative? It doesn't matter. Okay. So our goal is the change itself. Change in positive direction. In the negative direction, it doesn't matter for us. So how we can translate the word doesn't matter. Is there another way to translate this word? Doesn't matter. If I have information or error, and I don't care if it's positive or negative, how I can remove this sign? Come on, it's programming. It's not programming, it's math. Absolute. Take the absolute, the modulus of the value. So it doesn't matter if you are working with positive error or negative error. The difference will be the same. So why we didn't use the modulus here? Why we didn't use absolute value rather than square? Any thoughts? Okay, let me get you back to the gamma enhancement that we covered before. Half square equal what? Equal? Two square equal? So if the error is small and you square it, what will happen? It will be smaller. If the error is big and you square it, it will be what? Bigger. So this way I'm amplifying the errors. Okay? So if the error is already small, I will make it smaller because I don't care about the small errors. I want to catch the big errors or the big differences. Okay? So if the difference is small, I'm squaring it. I'm making it smaller. I don't want it. I don't want to see this smaller difference. I want to see bigger difference. Okay? So I don't want to catch this. I want to catch this. That's why we used the square rather than the absolute. Okay? So we will find the error between the newer window and the older one. Can we do this manually? The answer is yes. So assume that I have image like this. So this is 1, 2, 3, 1, 1, 10, 11, 5, 3, 20, 25, 50, something like this. So I decided to make this I window a 3 by 3. In this case, the initial window will be this. Then I will shift this window with a value of U and V. Again, U and V can be any positive value, bigger than or equal 0. Okay? Let's shift it with 1 pixel for U, 1 pixel for V. Okay? What we'll do is subtract any value in the blue from the similar value of the green. So it will be 1 minus 1 equal 10 minus 2 equal 25 minus 1, 50 minus 10, 100 minus 3. And so on with other. And for every value, I will square it. Okay? This way, I can easily catch the difference between them. Is this clear? Any problem about that? Okay. Now, to do this, I need to start from the top left corner of the image and specify specific value of U and V, choose value of U and V, like as we did here, 1 pixel, can be 1 pixel, 2 pixel, 3 pixel, depending on the size of our window. But of course, it has to be not bigger than the window size itself. Then I have to do shift over all the image to do that, right? Is this a good thing or a bad thing? Like, is it small task that will take short time for calculation, or it's a big task that will take long time?
Big task.
Because I have to scan over all the x's, then I will do over all the y's, right? Keep shift this and shift this window with it. So I'm shifting 2 windows with me. Is it something easy? No, it will take long calculations. That's why we thought about using technique to approximate this. Something that make our life easier in calculation. How did they decide to do this task or this approximation? By using something called Taylor expansion. What is the Taylor expansion? Taylor expansion is a mathematical technique we use to approximate any function. So in 1D, if you have any function f of x, I can approximate this function as addition of polynomials. So it can equal n equals 0 to infinity summation for n equals 0 to infinity of n of a times factorial a. Sorry. No. Factorial is here. Times so I will find the derivative of this f n times, and for each n value, I will make substitution with the value of a that I'm approximating this function around it, and we'll keep add those terms together. What does this mean? Let's take a small example. Assume that we have sine. You know the sine function? Assume that I want to approximate this sine function around the point of 0 here. Okay? Using polynomial. Can I do that? Yes. First, my a in this case will equal 0. First step. What is the value of sine 0? 0. Then I will find the derivative, first derivative. What is the first derivative of sine? Cosine. What is the value of the cosine at 0? Then I'll calculate the second derivative, which will be minus sine. In this case, the value of minus sine 0 will equal 0 as well. Then third derivative. And keep doing this again and again. Now, according to those values, I can say that the value of sine x around the 0 will equal, first, the value of sine 0 over factorial 1. Plus the first derivative at 0, which is 1, over factorial 1, x minus 0, plus the derivative, this over factorial 2 times x minus 0 squared, plus minus 1 over factorial 3, x minus 0 power 3, and so on. So this term is 0, this term is 0, so it will end up that I have x minus x cubed which is called Taylor expansion of sine around the 0. I can do this for any function, sine, cosine, exponential, any function that you want, you can do the same thing for it. Okay? Now, how this can help me to approximate this function. This said, here we are doing a shift around the value of x with a smaller derivative or a smaller shift u and v. Now, if you go back to the function or the definition of function here for the sine, around the zero here, if the function is too small or the value of x is too small, let's say it's 0.1. Something like this. In this case, 0.01 cube will equal what? Or something, like it will be 0.60501 power 5 10 zeros 1. So the number here decrease, right? So I can say with a good confidence that f of 0.01 equals sine 0.01 almost equal 0.01, which is the first term, which is the x. Right? So I can ignore those terms and say that sine x almost equal x if x is too small. Agree with that? Let's do it here. We will do the same Taylor expansion that we did for the sine, but for this function. The only difference is this is 2D. And we will assume that this u and v shift are tiny, very tiny shifts. So in this case, it will equal the value of I, x, and y plus, in the original, it's the derivative of the function with respect to the variable itself at this point. Here I have two dimensions. Then I have to find the first two derivatives. Then this multiply times u, this multiply times v. Again, this should be divided over factorial 1, and this is over factorial 1. Then I should have the higher derivative. Because for the second derivative, I have three derivatives. The derivative, the second derivative with respect to x, second derivative with respect to y, second derivative with respect to xy. Okay? Plus, I can still go with the third and fourth derivative. Now, as I said, the value of u and v is very tiny, small. So if I put them to the power or multiply them together, we will have the same exact problem I'm having here, right? So it's okay to say that I can ignore them. So those almost zero. I can ignore them. They are useless. Okay? So in this case, I will approximate this to equal I of x and y plus the first derivative times u, the first derivative times v. Now, this one looks okay for me, but we need to twist it a little bit to look similar or in the linear algebra form. In this case, this will have nothing to do with it, and this one it will be converted to first derivative of I with respect to x and first derivative of I with respect to y times u and v. So this become a vector form. Now I will substitute with this in the original equation. So I will remove this and make my substitution. In this case, this will cancel this. This is positive, this is negative for almost the same value. It will end up that I having IXU plus IYV all squared. This is second order expansion, bless you. So I will expand it. If you expand it, you will have IX squared U squared plus IY squared V squared plus 2 IX IY UV. Now, I will take the sum of IX squared and I will call it A. I will take the sum of IY squared and I will call it C. And I will take the sum of IX IY and I will call it B. So the summation now included inside those A, B, and C. So the equation now become like this. A U squared plus 2B UV plus C V squared. Why the summation disappeared right now? The summation is the summation over X and Y. Does U and B have nothing to do with X and Y? It's the shifting value. So no matter what is the value of X and Y, U and B are independent from that. That's why the summation removed or gone with the IX and IY values. Now, what is this shape? If you look to this shape, what it looks like?
It's square root square. Yes, with square root.
What is it?
Equal below the square.
A plus B all square, which looks like what? What is the shape of them? Geometrically, how it looks like? What is it? Parabola, but in 3D. So it looks like this parabolic shape, but 3D. Something like, you know, the parachute. It's exactly like the parachute, but inverted. Something like this. Okay? That concave up. So if you want to look X, Y, and Z, that's how it will look like. Something like this. Okay? Now, this shape, if I cut it with a plane like this, what is the cross-section shape? I said it's parabolic, right? But what is the cross-section of this parabola?
Same as the top.
What that?
Same as the top.
Which is?
Round.
So we
Round?
Like.
So I'm saying it's a circle?
Yeah. That's
All of you agree with that? Actually, it's not a perfect circle. It's an oval. Okay? Ellipse. So that's how the curve will look like. But if you cut it with a plane, you will see ellipse. Okay? Now, our goal is to have bigger error or a smaller error. What are we searching for?
Bigger.
Good. Don't forget the main goal for our work. We are looking for the area that has maximum error. Because if I have maximum error, in this case, I have a corner. So I'm not minimizing here. I'm looking for the area with maximum error. Okay? So my goal is to find the area in this shifting that had the best error, the maximum one. Okay? So I'm not optimizing here. Watch out. Okay? Because the same shape of that, like the function that we optimize for the deep learning, but this is completely different. Here, I'm looking for the maximum error I can achieve. Because if I have maximum error, I have a corner. If I have low error, then there is no corner, it's a flat error. Okay? Okay. Let's reorganize this equation again. This equation, if we reorganize it, it will look like this. This vector is 1 by 2. This vector, or this matrix, is 2 by 2. And this vector is 2 by 1. If you multiply this time this time this, it will end up that we have this one, which is 1 by 1. Okay? This matrix in the middle, we will call it the H matrix, where it's a matrix consists of the value of A, B, and C. Is this matrix symmetric or no? How do we know the symmetric matrix? Put your hands in the main diagonal and check the up and down. Are they similar?
Yes, yes.
B up, B down. So it's symmetry. Look. Okay? So this is a symmetric matrix. What is the dimension of this symmetric matrix? Who agree with that? Who disagree? It's a Boolean, yes or no? What, do you have another fuzzy state in the middle? Who agree? Who disagree? This matrix is always 2 by 2. Why? First, this is scalar. It's not a vector. It's an error value. So it's a number. Okay? So those are numbers. This is a scalar. This is a scalar. This is a scalar. So the H matrix will be always 2 by 2. It can't be ever bigger than that. Okay? Now,
You said if you do it diagonally, it's what is it called?
symmetry.
Yeah, but what if you do it the other way?
Well, we are judging the symmetry
Just
by the main diagonal element. So those are the main diagonal. We look up and down. This is not the main diagonal. So this is not the judgment for symmetry.
they don't need to.
No, no, no. Okay. Okay. Now, assume that, or as we agreed before, we are looking for the maximum error, not the minimum. We are not minimizing it. So I need this curve to be as big as possible, as large as possible. Okay? How can I know that? How can I know if the curve, this curve or this surface is big or small? Can I judge from this equation? They said yes. How? Let's take a smaller look. If the value of A and B have special cases. Like if A equals 0 and B equals 0. In this case, if this is 0 and this is 0, in this case, I have only change around the Y direction. So the curve, instead of look like this, it will look like a cylinder. If you cross section it, it's real parabola. Okay? Now, this is those are the main axes. Now, assume that you are moving in this direction. So you have frame like this, and this frame is moving in this direction. Do you see any change? No. So the derivative on the x direction is 0. On the other hand, if you are moving in this direction, it's already parabola. So there is a change or no? Yes. So this is my x, and this is my y. So the derivative over the y has a value, but no value for the derivative over the x. This can happen when? If you are moving over a line. So a special case for this equation, if a equals 0 and b equals 0, this means that you are moving over horizontal line. What if you are moving over vertical line? I think you can guess right now.
The opposite.
Exactly. So it's exactly this shape, but rotated. So,
Oh, well, both of them, or just? Well, yeah.
okay. So in this case, the derivative in this direction, which is the x, has a value, but the derivative in this direction of the y has no value, 0. If you move in this direction, it's the same exactly cross section, no change. Only the change in this direction. Okay? So in this case, I will have only a, and the value of b and c will be 0. Can I use those concepts to judge if I have a corner or no without make all the shift that we discussed before? Without going with all this window shift? Can I use the concept that we discussed right now to find the corner?
Yeah.
How?
All have a value.
Only if they have a value? This is something good about this H. As I said, if A equals 0, we have this case. If C equals 0, we will have this case. What if both of them has values? So in this case, A, B, and C will have value. Can we judge them by checking only H? They said yes. The cross section of the curve, as I said, it looks like what? Ellipse. Okay? The parameter for those ellipses will be, sorry, B and A. The two diameters of the ellipse, right? The ellipse has two diameters, the bigger one and the smaller one. This bigger one equal 1 over the value of lambda minimum of H. The smaller one will equal 1 over the square root of the lambda maximum of H. It's lambda. Lambda are the eigenvalues of the H. What does this mean? What's the meaning of eigenvalue? From math. If I have any specific matrix, A, I can calculate two things for this matrix. The first thing called eigenvalue, the second one considered or called eigenvector. What is the eigenvalue and the eigenvector? The eigenvalue and the vector considered to be measurement for how strong this matrix in specific direction, and this direction is X. So for example, if you have a matrix, get this way. Something like this. If you have a vector like this, okay? In this case, I can solve this one into two components. One in this direction and the other in this direction. This, or the component in this direction, I can consider it as the first eigenvalue for this one. The second one here, I can consider it as the second eigenvalue for this one. The value of this length is the lambda 1, because corresponding to this vector. The value for this one can be considered as lambda 2, because it's the corresponding value or the length for this vector. Okay? So x1 and x2 can be considered as the unit vector in the direction of projection. Okay? But of course, it's more advanced a little bit. I'm giving you a very simple example with 2D vectors. Okay? But usually this is a matrix. And what is the corresponding, or what is the condition for the matrix to have eigenvalues and eigenvectors? It has to have two conditions. First, has to be square. Only square matrices can have eigenvalue and eigenvectors. Second, it must be invertible. You can find the inverse of it. Okay? If the matrix satisfies those two conditions, in this case, the value of the eigenvalue will equal lambda here in this equation, and the value of eigenvector will be x here in this equation. How can I find the value of lambda on x for this matrix? They said simply, I will try to simplify this and solve the equation for the variables. How can I do that? They said simply send this to this side. So it will be ax minus lambda x equals 0. And the 0 here is the 0 vector. Now, I can take x as a common factor. But again, because this is a matrix or matrices operations, I have to take the common factor from this direction. So it will be a minus something times x equals 0. I take it from here, so it will be a times x. Now, when I take the x out of here, it will be lambda. But times what? I still need something to satisfy the matrix operation. This said, make it I, the identity matrix. Okay? So now I have a minus lambda I times x equals 0. Excuse me. What is the value of x here? This is a 0 equation. Something times x equals 0. What is the value of x? X can't be 0. That's why I need this lambda. So the lambda 1 or the lambda value must satisfy the condition that x is not 0. How I can guarantee that x is not 0? This equation must not be invertible. So I can't send it to the other side. Meaning the determinant of this equation must equal 0. If the determinant of this equals 0, I can't invert it and send it to the other side. So x cannot be 0 by any chance. Okay? So I calculate the determinant of this one. Again, as we said, A in this case is our h. And h always has a dimension of 2 by 2. It will never change. So if we assume that h will equal h11, h12, h21, h22. Those are the elements of h, which are the A, B, B, and C. So the same exact elements. The A is h11, the B is h12, and so on. Now, I will subtract h11 minus lambda I. h12 minus lambda I, this will be 0, so h12. h21 minus 0. Then h22 minus lambda I. Then I calculate the determinant of that. You know how to calculate the determinant, right? It's 2D, 2 by 2 matrix. In this case, the determinant is this times this minus this times this. So it will be, I write it here. It will be H11 minus lambda times H22 minus lambda minus H12 H21. Now, I can extract this and find the equation for that. So it will be H11 H22 minus H22 lambda minus H11 lambda plus lambda square minus H12 H21. If you arrange this equation, it will equal lambda square minus H22 plus H11 lambda plus H11 H22 minus H12 H21. And all of this must equal 0. I already know the value of H11, H22, H21, and H12. So those are known. I know this, 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 I know this. What exactly the unknown here? The lambda. So I can solve for lambda in this equation, which is a second order equation. Okay? So I can use the general rule for the second order. In this case, the value of lambda will equal this form. Very straightforward. You can easily apply the rules, the general equation for the cubic rule or the cubic equation for this case. You will get this equation. Okay, so now I'm having two lambda values for this H matrix. As I said, one of them will be big and the other will be small. The value of A, which is the bigger diameter, will equal 1 over square root of the minimum. The smaller diameter will equal 1 over square root of the maximum. Which makes sense. If this is big, then 1 over square root of it will be small. If this is a small, 1 over square root of it will be the big one. Okay? Now, this lambda minimum and lambda maximum, both of them large. In this case, I will have large value or smaller value of A and B, which will make the curve small. If they are small, I will have large value of A and B, and the curve will be big. So from this concept, I can determine if this point is a corner or not. So I don't need to do a shift. So this shifting process is useless for me right now. All what I need to do is to find the H value and solve for the eigenvalues. Once I solve for the eigenvalues, I can easily determine if it's a corner or no. So always the value of X maximum, which is the eigenvalue, eigenvector, will be corresponding to the lambda max. The value of X minimum will be corresponding to the lambda minimum. And each one of them control one of the diameters of our ellipse. So now I can understand any area or any shape I'm having and determine if it's a flat surface or if it's a line or if it's a corner. So if the two lambdas are closer to each other and both of them are small, in this case, I'm having a flat area. If two of them are close to each other and both of them are big, then I'm having a corner. If one of them bigger than the other, it doesn't matter which is bigger than the other. One big, one small, in this case, I'm having an edge, a line. Okay? So no need to shift, no need to do anything. Just solve for the eigenvalues. Okay? So our goal right now is to find this H matrix and solve for it for any single area, then find the eigenvalues. Based on these eigenvalues, I can judge if this area is a corner or flat surface or what. Is this clear? Now, let's see practically how this will look like. If we assume that we have this chessboard and we apply all what we discussed right now over it, we will find that the value of lambda maximum will look like this. The value of lambda minimum will look like this. This means the corner is obviously where? This is a corner, right? This is the corner. This is the corner. If you look to this and this, which number or which lambda value can give me the corner? The minimum. Because if you remember, the minimum, the one that control what? The bigger diameter. So if I have large minimum, I will have bigger diameter, so I can have a corner. Okay? So for this, find the h's, and for each h value or h matrix, find the minimum and the maximum lambdas. Based on that, find the maximum value of those lambda minimum. Congratulations, you found the corner. Okay? So the steps to solve for it is easily by finding the value of lambda maximum and lambda minimum for the H matrix. And I'm trying to find the maximum value of the lambda minimum that satisfies my condition. Now, the problem with this technique is very tiny. What is this? If you look to the lambda minimum, that's how it's shaped. So it's not one value, no. It's a cloud of points. And this cloud of points has minimum, maximum, minimum, maximum, minimum, maximum. You see this black shadow in the middle? Then how I can solve this black shadow? This said threshold. Find the threshold value or add a threshold value here in this curve. And based on this threshold value, you can find the maximum point. So the steps will be like this. I will calculate the gradient at each point of the image. Why do I need the gradient? Remember, what is the value of A, B, and C? A is the summation of ix squared. B is the summation over ix, iy. C is the summation of y squared. What is the ix? It's the derivative of the image with respect to x direction. What is the iy? It's the derivative of the image on the y direction. C is the multiplication of them. So the first step in my calculation must be calculating the gradient. Then, for those gradient, I will start to group them by the window size. Sorry. I will start to group them by the window size, U and V. And for each window size, I will calculate the H matrix. For this H matrix, I'll calculate the eigenvalues for it and find the lambda minimum, threshold it. And if the value of the minimum bigger than the threshold, this is a corner. Is it clear? So the steps as follow. I will give you the image. First step, calculate the two gradients. Gradient in the x direction, gradient in the y direction. Then you have to determine the window size. This window size will determine your U and V, the size of your window, the shift that you did. Then for this window size, I'll calculate the H. For this H, I'll calculate the eigenvalues. And we'll take the minimum eigenvalue for the H and we'll compare it to the threshold. If it's bigger than the threshold, it's a corner. If it's lower than the threshold, it's not a corner. Is this clear? Yeah. This concept was good, but this thresholding problem became a big challenge or somehow challenging. So they decided to change it a little bit. How? By defining something called Harris operators. What does this mean? It means that I will not work with the lambda minimum only. No. I will make a function between lambda minimum and lambda maximum. Combine both of them. Because if you look here, the point that lambda minimum is maximum, exactly the same point that lambda maximum is what? Is minimum. So why should I use this alone? I can use this only. I can combine both of them and normalize them. And that's exactly what Harris found in his operator. So he said, I will work with both lambdas. And I will define my operator, which I will call F. It will equal lambda 1 times lambda 2 over lambda 1 plus lambda 2. Which one is minimum and maximum? Doesn't matter. No difference. I don't have to keep searching for which one is minimum, which one is maximum. No, I will multiply them, add them. This is my operator. Now, if my operator is bigger than specific threshold, it's a corner. If it's smaller than a specific threshold, it's not a corner. Now, should I calculate the lambdas to find those two values? They said no. Why? Actually, the value of lambda 1, lambda 2 equal the determinant of the matrix H. The value of lambda 1 plus lambda 2 equals something called the trace of matrix H. What is the trace? Trace simply is the sum of the diagonal elements. Meaning, in this case, lambda 1 plus lambda 2 equal A plus C. Always. It's not a special case. Okay? So I don't need to find the lambdas. And lambda 1 lambda 2 equal determinant of H, which is AC minus B squared. So why do I need to find the eigenvalues in this case? So calculating the eigenvalue will be extra time for calculation. Just calculate the trace and the determinant and divide them over each other. You got the Harris operator. Okay? So this one will have the same effect of using the lambda minimum, but less expensive because we remove the execution time or the calculation time of what? Of the eigenvalues, which is actually take time. It's not something simple that we can do. Okay? This concept was okay for a while until they found one more concept or one more operator and call it alternative Harris operator. For this operator, they said, I will use the same exact concept of determinant and trace, but I will not normalize them. I will add them. Then I will add some hyperparameter K. This parameter will be used for the threshold. So I will find the determinant and multiply the square of the trace times K and subtract them from each other. And after that, I will find the maximum value in this value. This is actually the one used recently in all calculations. So if you are using or you are working for corner detection with any toolbox, you will find that they are working with this Harris technique. Okay? And this concept, fine or more sensitive for the corners, means it can find more corners. Okay? Compared to the other two. So if you want to look to the Harris operator or the modified Harris and the value of lambda n, this is the value of the lambda minimum. And this is the value of the Harris operator. As you can see, they are close to each other. This one is more accurate a little bit, but this one looks similar to it, and we can find the minimum in the middle with less calculations. So this one requires less calculation. This one is better, but more expensive in the calculations. Okay? So we can now test on some real image. So we will have any image we want, and we will start first, as we stated, by finding the derivative. So I will find the derivative for both images. How can I find the derivative? How can I find the derivative? Ix. Are you sure you finished assignment 2?
I'm not that much correct.
Subtle.
So,
Subtle filter. Remember, we said that we have subtle filter that can be used to find the derivative. So Ix and Iy are nothing but the output of subtle operation. Okay? So the first step is to find Ix and Iy using the subtle filter. Then for these derivatives, I will have window size of a specific fixed size U and V and calculate both A, B, and C. Then from this edge, I'll calculate the Harris operator or modified Harris operator, depending on the one we are using. Okay? Then shift, do the same thing. Shift, do the same thing. Shift, do the same thing until I finish the whole entire image. So this way, I'm shifting over the image only once. There is no double shift like the subtraction that we did before. If we try to calculate the Harris operator for this image, that's how it will look like. So you can see these spots have the maximum value of F. So high, 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 high. Now, how can I find the maximum value within this? I will start by thresholding. As you can see, the thresholding here give me spot. Didn't give me an actual point. Remember, I'm looking for a corner. Corner means point, only 1 point. So did I receive a point here? No. How I can find the point? How I could find the edge? Remember the edge? After the high pass filter. After we apply the supple and find the magnitude, we did something.
Subtracted the change.
Not maximum suppression. Find the maximum direction. Okay? We calculate the magnitude and the angle. Then we go to the direction of the angle. The non-maximum suppression to find exactly the maximum points. Okay? This maximum point is our corner. Okay? If we apply this, can you see the dots? If we apply those dots to the image itself, it will be those red lines. Okay? Now, you compare those two images. Did we have the dots in the same exact place? So for example, here I found a corner. If I compare the same area here, did I find a corner? Yes. Here I found two corners. Did I find two corners here? Here I found a corner. Here I found a corner. Did I find any corner here corresponding to it? A problem. Here I found corners. Did I find any corners here corresponding to it? So this is one of the drawbacks of the corner technique. One of the drawbacks, which is it's not invariant, or it can't resist illumination change well, and can't resist 3D view well. You see the difference between this and this is what? 3D view, rotation, 3D rotation for the head. This one is a complete 2D. This one has a rotated one. Okay? This one has a high illumination. This one has low illumination. So this technique worked good, and I could find the corners, but the corner technique in general has some drawbacks, and we will talk in details about this later. Okay? We said this technique worked well until they found some fine-tuning way to it, which is what they said. If you look here for this one, yeah, this or this. Do I need all this area around the corner, so the corner mainly in the middle, do I need all this area around the corner to find the corner? When I'm using the window and shift it. So this is the window, and I'm keep shifting it, right? Do I need all those points around this point or this region to find the corner? They said, no, not really. So I can give higher priority to the middle and lower priority to the points around it. What does this mean? It means that I can multiply it by weight. So each H matrix can be multiplied times a weight matrix. This weight will give higher priority or higher weight to the point in the middle and lower priority to the points around it. This look familiar to you? Yes. Here. This is a Gaussian filter. Give high priority to the middle, lower to the value around it. Okay? So this is the main concept of the Gaussian. So we are multiplying the value of H times Gaussian value, and we sum over it. What is the name of this operation? Multiply over the values and sum. Exactly. So we are doing convolution here. So based on that, we can conclude the process of the corner detection as follows. First, I need to find the second moment matrix, which means the value of Ix and Iy, then calculate the II square, the Iy square, and the Ix Iy for the whole entire image. Okay? That's what we call the second moment. Then I will have my shift window, and this shift window will be convoluted with a filter to give higher priority to the middle, lower priority to the sides. This will give me my final H matrix. So this is the first derivative, Ix and Iy. Then I calculate the second moment, which is the second derivative, not the second derivative, the squared value of Ix Iy and Ix Iy. Then I apply the Gaussian over them. After that, I'll calculate the H matrix. For the H matrix, I'll calculate the determinant and the trace. Again, I don't have to do this through the eigenvalue. I can easily do that by having determinant to be AC minus B squared, and the trace would equal A plus C. Then I will use non-maximum suppression, calculate the operator, the corner operator using Harris corner operator or modified Harris or whatever operator we decide. Then I will apply non-maximum suppression to find the center of this maximum point. And this center will be my corner. Okay? So that concludes our corner detection algorithm. This corner detection algorithm actually called Harris corner detection, which has been published 1988, but still in use until the moment. And it's very popular when we are looking for good features or good points of interest in a given image. Okay? Any problems? Any questions so far? Okay. Now, as I said, Harris is still in action, yes, but it has some problems. What are those problems? Assume that you have corners that's a little bit rotated. Will you be able to find those corners easily? The answer is that you have some troubles with that. And also, sometimes you can find the corners in between the areas. So it's not a straightforward technique to find some corners. That's why they decided to use another algorithm or another operator again. So the same exact algorithm called Chai-Tomsky operator, which is a modified version of this original. Harris, but it's easier for calculations. Unfortunately, this Chai-Thompson algorithm, even if it's working good and faster, but it failed to detect lots of the corners. Okay? But it's faster than the traditional Harris operator. So the Harris operator is slower a little bit for finding the corner, but it can find more corners than Chai-Tomsky. Chai-Tomsky is faster, more default, but can find low number of corners in the image. If we go back to our problem initially, which is this problem, is it better to find low number of corners or high number of corners?
No.
You are saying low?
Yep.
Why?
Because we can construct the image from less also. That
Because
we can construct the image from less corners also.
sorry, what does this mean?
I mean, we don't have many distinct features in the image.
If you have lower number of corners, this means you have many distinct features?
Are you saying you don't have?
Okay, if you have lower corners, this means that you have lower distinguished feature, right? So is this a good thing or a bad thing? Okay, so it's better to have more corners. If I can find more corners in the image, that means that I can easily find the matching. The possibility of matching is higher, right? But how about the calculations? Because remember, I'm now still in the first step. Next step will be what? Finding the feature around each corner. So if I generate lots of corners, means that I have to generate lots of features around those corners, which will consume more time from me. So it's a trade-off. There is no absolute good or absolute bad. Okay? Depend on your system. If you have the capability to generate or to have lots of numbers or lots of corners and calculate features around them, please do it. Okay? Because that will be good in the matching process. If you don't have the capability and the machine you are using is lower latency, then try to find the optimal number of corners that you can use to do the job. Okay? So don't try to increase the number of corners just for the sake of increasing the corner. No. Try to balance between the number of corners and the features around them and your calculation power. You should be balanced between both of them. Okay? Any questions so far? Okay. So so far we learned about the edge detection. How can we detect the edge in a given image? And we learned about the corner detection. And we defined the corner, and we learned how can we detect the corner in a given image. Now, as we stated so far for the beginning part of the course, we are trying to avoid using any of the toolboxes that do those tasks. So our goal is to work and find the edges and the corners ourselves in the code from scratch. Okay? So how can we do that? Actually, this is the code that can do this task. So if you recall from the Canny edge detection, we said what is the first step to do before finding the derivative? Let's review the first step in the Canny edge detection. First step should be applying Gaussian filter, okay? To make sure that we are removing all the noise in the image, right? So we need to have a Gaussian filter with a specific size. You need to have a Gaussian filter with a specific size that can use for the filtration. By default, the value of sigma and mu for the filter, sigma is 1 and mu is 0, okay? But you can adjust those values depending on the size of your kernel. So those values are suitable for the 3x3. But if you're having more or larger kernel, in this case, you need to increase the value of sigma and mu. The mu mostly will be 0, but the value of sigma need to be adjusted depending on the kernel size, as we discussed this before. After we calculate or generate the Gaussian kernel, we have to do the kernel or the Gaussian filtering to the image to remove any noise that we have in the image. But before doing that, we have to make sure that the image is a grayscale image. We are not working here on RGB. The image must be grayscale. Okay? How we apply this Gaussian filter? Again, it's the convolution process that we used before. Remember this convolutional filter or convolutional process that you did in a previous assignment? So it should be the same one. Okay? Then I have to apply the Soppel filters. I have to apply Soppel in the X direction and Soppel in the Y direction. The value of the Soppel filter you already know. So you can easily apply it using, again, the convolutional process. Convolution 2D. Okay? After that, we will calculate the magnitude and the angle of the derivative, the S and the theta. Okay? For both of them, we will calculate the non-maximum suppression to find the direction of the maximum value within the direction of the maximum value within the magnitude. Okay? So we'll calculate the magnitude of Sx and Sy between Sx and Sy. Then we'll calculate the angle between Sx and Sy and use this angle to find the direction of the maximum value. Okay? Again, here we are not using interpolation, we will use the 22.5 rule. Remember the 22.5 rule to make 45 degree? This is the rule I'm using this here in the code. Again, if you want to use the interpolation technique, feel free to use it. After using the non-maximum suppression, we will do the thresholding. Remember, with the canny edge detection, how many thresholds we apply? Two thresholds, higher threshold and lower threshold. If the value of the magnitude is bigger than the higher threshold, this means that this point is an edge, no matter what. It's a strong edge. If the value between the higher threshold and the lower threshold, it's a weak edge. If the value is smaller than the lower threshold, then it's not edge at all. Right? Based on that, we will apply the hysteresis process, which will find the relation between the weak threshold point and the high threshold value, or the value bigger than, or the strong edge and the weak edge. Okay? If the weak edge is connected to strong edge, in this case, the point will be an edge. If the weak edge is not connected to strong edge, then it's not edge at all. Okay? Based on that, we can calculate the hysteresis and determine if the edge or the image or the edge is an edge or it's a weak edge, we can ignore it. If you do all of this process, that's what you will get. So we are working with one. So this is the original image that we are working with. First, we are converting it into grayscale, the first step. After that, we are do Gaussian filtering over the image. You can see the difference between this, the non-filtered, and the filtered version. You see this one? It's too sharp. This one is blurry a little bit. Okay? Then we will find the gradient over the x direction and y direction. With too much windows. We will find the gradient in the x direction and the y direction. And based on that, we will find the magnitude of the gradient. Is this an edge? Is this the final result of the edge image?
No,
Why?
it must be 0 or 1.
Exactly. The edges are binary image. It's not, doesn't have any value. This one has value. It still has grayscale value. Okay? So this is the result after applying the non-maximum suppression in the direction of the maximum gradient. Again, at this edge, not yet. Now, after applying the canny edge detection and find the hysteresis between the strong edge and the weak edge, that's exactly what I'm expecting to happen. This is now a binary image. As you can see, it's clear. We have ones and zeros. Okay? How I can change those edges, increase the edges or reduce the number of edges? As we stated last time, what are the parameters I need to play with? As we stated, we have two parameters, or literally three parameters. This parameter, sigma, for the initial filter calculation. Okay? If I increase the sigma, this means I'm reducing the number of edges. Reduce the sigma, reduce the number of edges. Okay? Sorry, reduce the sigma, increase the number of edges. Increase the sigma, reduce the number of edges. The second, two other parameters, the higher threshold and the lower threshold. If the value is higher than the higher threshold, in this case, it will be strong edge. So no matter what, it's a strong edge. If it's lower than the lower edge threshold, then it's no edge no matter what. So those two parameters, I can adjust to control the quality of my generated image. And if you check the library of OpenCV, you will see that those three parameters are hyperparameters that you apply as an input to the algorithm. Okay? I don't have to remind you that OpenCV is not allowed here. You're not allowed to use any of the OpenCV algorithms. Okay? And if any of you use the OpenCV, this means that the final grade or the grade of the assignment will be 0. Okay? Now, same thing now can be applied to the Canny. Sorry, Harris. The Harris corner detection. We will do the same exact steps that we described or we will work on here in the lectures. First step, we will read the image and make sure that the image is converted to grayscale. Because again, for Canny edge detection and the Harris corner detection, we are not working with color image. The image must be grayscale. Then I have to define the value of K, which is the value of the constant in the Harris operator, or the file Harris operator, and the value of my threshold. Because the value of the operator, if it's higher than the threshold, it's a corner. If it's lower than the threshold, it will not be a corner. And I have to determine my window size. Remember, when I calculate the edge, I have to determine the window first to calculate the edge for this window. Okay? Based on that, first step, again, applying Gaussian filter. First step in all process. Why? Again, for removing the noise. Noise removal is a standard right now. After that, I have to calculate the gradient, the derivative in the x direction and in the y direction. Again, how we will do that? Exactly, using the Sobel filters. After that, we will find the second moment, I squared, Ixx, Iyy, and Ixy. Excellent. Then we will start by the initial window place and start the calculations. This is the calculation of the offset, which is the center point that I will shift. Okay? Then, for each window size, I'll calculate the value of Ixx for this window size, Ixy for this window size, Iyy for this window size. For each one of them, I'll calculate the sum. This one is A. This one is C. This one is B. I will use those three values to calculate the determinant and the trace. As we stated, the determinant is AC minus B squared. AC minus B squared. The trace is A plus C. Next step, calculate the operator and store this operator in the operator matrix or the operator value. Then I will use it later for visualization and judgment. After I finish the shift over the whole entire image, I will start now to judge the operator. The operator value normalized. So this is the step of normalization. Remember the normalization process that we discussed at the beginning of the year? How you can do normalization? If you have an image and you want to normalize it, how you normalize it?
By 250.
I'm sorry?
By 250.
How to normalize image? The min-max technique. So remember the histogram? The value subtracted from the minimum divided over the maximum minus the minimum. Min-max normalization technique, the one that we use for the histogram. Okay? This way, I guarantee that the value will be between 0 and 1. After that, I can threshold them and find my corners. So if I do so, do I finalize the other one or no? Yeah, it's still calculating because I'm running over the whole entire image. I'm calculating the operator. As you can see, it found the corners in my image. Okay. What are the parameters that determine the corners in the image? If I want to increase the number of corners, what should I do?
Yes. Decrease the.
Exactly. So the first thing, decrease the value of the sigma used in the first step, this Gaussian process. Decrease this Gaussian value. This is the first step. What else?
Thresholding.
Is it?
Thresholding.
Exactly. This threshold. Okay. What else? Okay. Yes, it can affect, but not that much. But there's another parameter also that I can play with. K. Remember, the operator itself has a hyperparameter K now. Okay, so we can choose a value of K that can change the value of the corners, so it can show the corner more. Okay, so change the K value, change the threshold value, change the sigma value, and finally changing the window size. All of those can affect how many corners I can find in my image. Okay, is this clear? Any questions? Okay, so I think you are ready now for next assignment. At least you have something to work on during the spring break. Now, are the corners considered to be the only type of features I can extract from the image? As we said, no. We can also extract the blocks, right? But can I extract lines as well? What do you mean by extracting line? We learned how we extract edges, right? Does extracting edges means I'm extracting lines? Does extracting edges means I'm extracting lines?
And
Okay. So if I extracted something like this, is this edge or no? Is it a line? So extracting edges is something, and extracting lines is a completely other thing. Okay? Edges are edge. So this is edge. This is edge. This is edge. This curvature is edge. All of those considered to be edges. Are all of those lines? No. So when I say line extraction, means I want to extract the mathematical equation of the line in the space. What is the mathematical equation of the line in space? If I want to write a mathematical equation that describes a line. Well, so the general form is ax plus by equals plus c equals 0. Or y equal mx plus b, where m is the slope and b is, what is this constant? Anyone recall? The y-axis crossing. So this is b, right? Now, the question is, if I give you edge, can you give me from that edge the equation of the corresponding line? Here exactly what I'm really looking for. If you have an edge, which means number of points, just points, can you from those points extract the corresponding line equation in the space? Actually, this task is not an easy task. It's an exhaustive task. Why? First, the points will never be aligned. So you will not have a perfect line ever. Okay? Second, the points usually have noise. So they found or they proposed several techniques to do this job. So assume now that you have points looks like this. And I want to extract the lines in this equation. How many lines I have here? Without applying any algorithm, just by your eye. How many lines we have here? Okay, one say one. Who agree with that? Who agree with one? Who agree with two? Who agree with three? Who agree with four? Okay, who agree with four? Who agree with five? Actually, here we have three lines. Line, second, and third. Okay? How about this? This is a noise. Point that has deviated from the correct direction due to noise while I'm capturing the image. Now the question is, how can I find those three equations? They said it doesn't matter how many lines you have, I will start by the two ends of your points. Those two ends. I will connect them and find the line connected them. Very straightforward. If you have 2 points, can you find the line connected them or no? Straightforward. This is algebra 1 in middle school. So it's not something tough that you can do. So point and point, connect them and find the point, the equation of the line, connecting them. Then split that line. Split it with the point at maximum value you have. Can be from the middle, can be from any other point, but it should have the maximum point in the middle. So this point will divide it into 2 lines. Then each one of those 2 lines will find the maximum point as well and split itself. Then I will have 1, 2, 3, 4. Then I will do the same thing with those points, which will give me 1 more line. Now, this line has no line intercept with it. This line has no line intercept with it. This one has 2 lines intercept with it. So I have this, and I have this and this. In this case, I will do merge, meaning those 3 will be merged into 1. The one that has the highest number of points, which is what? The one in the middle. This means ignore this and ignore this. This algorithm called split and merge. So I'll keep splitting. Then when I start to have multiple lines use the same exact points, I'll start to merge them. Okay? The technique is okay. But when we have large number of points, can you apply the same technique easy? Oh, it will take lots of time. Okay? Because we'll keep splitting, then merging. So this will take long time to apply it. That's why they said, I need another algorithm. So they thought about something called, or something that came from statistics called linear regression. How this works? They said, I will divide my points into subpoints. Those subpoints will be joined with a window. So the window will have a size NF. Then I will start from any direction you would like, it doesn't matter. Assume that we have this NF equal 3, 4, 5, it doesn't matter. Okay? I will join every 3 points in a line as much as I can using the linear regression algorithm, which means the line that I have to find must have the minimum error. If this line passed through the 3 points, it's perfect. That's exactly what I want. If it didn't pass with the 3 line, then should pass with 2 of them with the minimum error with the 3rd. Like here, this, and this. Those 3 points, are they collected with the same line? No. This one is away a little bit, but I'm trying to find either this and this, or this with the minimum error as much as we can. I will shift my window for the next 3 points. Try also to find the line that joined them. If you find one line, join them all, that's perfect. No, try to find the line with the minimum error. Then shift it again. Do the same thing. Shift it again. Do the same thing. Shift it again. Do the same thing. After that, we'll merge the overlap. Meaning, this line, and this line are overlapping. So I will merge them with one line. This line with this line and this line, so this sector and this sector overlap. So merge them in one line. That means that all of this considered as a one line, and this also considered to be as a one line. So we have here 2 lines on. This is what we call the linear regression technique. Okay? So I have a window size, which is I choose. Then within this window size, I try to build line equation as much as I can to merge them as possible, to combine them into one line. Again, is this a good technique? Sort of. Because this algorithm depends a lot of the window size. So if you apply n equal 4, you will get completely different result from n equal 3. You will get a completely different result from n equal 4, 5. So the result will differ with your window size. Is there any consistency with that? They said you can have consistency if you have randomness. So consistency and randomness work together. How come? You are working on some points from our space. It will be better than working with all of them. Especially that the number of points in real life, the number of points in real image or in real situation will be thousands, not millions. So will we have time to do all of these calculations? Answer is no. So can I use a randomness or random sampling to solve this issue? They said yes. And we will call this technique random sampling consensus or RANSAC, and memorize this name. What is this name saying? Saying don't work with your whole entire data set. Sample. With sampling, you will get resistance against the noise. But the problem is, if I sample once, can I have a good sample? Of course not. This means that you have to sample thousands of times. What does this mean? Let's take an example. Assume that we have those points. See this point cloud or those number of points? I want to find the line that go through those points. With your intuition, just with a look to it. Where is this line? Should be this one, right? How about all those other points? Nice, right? How can I find this line with all this noise if I'm doing sampling? As I said, don't sample once, you have to sample thousands of times. What does this mean? Assume that we will do random sampling, meaning I will generate any 2 points, just 2, no more than that. Because to build a line, you need 2 points. You need more than that? No, just 2 points give you the perfect line equation you want. So sample 2 points. This will have x1, y1, and this is x2, y2. Can you find the line that connect all of them together? Connect those 2 points together? Yes, straightforward. Substitute the equation. Then find that line. What's next? Calculate the error between the line you generated and all other points. Are all those points on that line or no? So I will measure the distance between the other points and that line. And I will build a table. For this value of M and B, I got this error value. Put it aside. Now, sample again. All the points within some specific threshold, I will accept it. So anything within this threshold, I will say maybe those are what? Error, noise. But all those far will not be considered as a part of this line that I built. Then, so any point within this threshold will be accepted. Anything outside will not be accepted. Then I will sample again. In this case, I will have another MB2 B2, which has another error value. So those are the correct value, and all those considered to be wrong. Then sample again. Again, build the third row in the table. Sample again. Keep doing this again and again and again and again until you have two values that lie on this cluster of points. In this case, if you calculate the value of the points and the error within this, you will find them the minimum one. After the specific number of iteration or a specific number of sampling, which is said with thousands, I will find that this one is the minimum. So this is the correct line. Which is the correct M and B. Y equal M correct. X plus B correct. This technique called RANSAC, which is built based on random sampling. This technique works only for finding the lines? The answer is no. This technique is very important to find the matching for optimization. So we will use the same exact technique later to find the matching between the features. Again, using the same concept. But instead of collecting 2 points and calculate the line between them, we will calculate 2 features or 2 points and calculate the distance between the features between them. So the concept of RANSAC is universal. It can be used in any application, okay? Because it's robust. It can work even if you have lots of noise. Okay? Now, if this is the case, can we use it for all our work? Answer is not really. Why? Again, we said that we have to do how many samples? Thousands, right? This 1,000 equal what? Can we sample all the possible samples? That's impossible. So if we have, for example, 1,000 points, sorry, 10,000 points, we want to fit with the line, we will find that we need to sample 50 million combination. Is this feasible? For now, no, but maybe in the future, yes. With the new chip that Microsoft proposed 2 days ago, there is possibility, maybe soon. So, this is considered to be infeasible if you are working with regular computers, okay? So, in this case, I have to put upper limit for my work. Is it guaranteed to find the correct solution within this upper limit? The answer is no. Unfortunately, it depends exactly, or that's upper limit that I will set to find the best solution. There is no guarantee that you will achieve the best solution within this subset. Sometimes you will, as we are sampling randomly, maybe you catch the correct sample with your with one of your sampling, maybe you will not. Okay, so no guarantee that you can achieve the best solution in that. Okay. For that reason, we moved to the fourth technique to find the line, which called hue transform. What is the concept of hue transform? This said, this is the equation of the line, right? Why should I represent the line with this equation? I can represent it with two parameters only. So M. I can represent it with M and B, right? Those two values can be considered as a point in the space. So if I have two coordination, one for the slope and the other for the y cut, I can consider any line as a point in this space. I will consider, or I will call this space a hue space. So the hue space is another geometrical space that has two dimensions, which are the slope and the y cuts. And any line can be described by one point only in this space. Okay? So if I have any line like this, I can represent it with only one point from this M0 and B0. Okay? How about if I have point here, which is X0, Y0? How it will look here in this space? How do you think? Then you define the point in the Euclidean space. Geometry. 70 grade or 20 grade. I'm sure which will be decided. What's the definition of points? The point is the intersection of two lines, right? So this point is the intersection of two lines, right? We agree that this line described here, let's call this one y equal m1 x plus b1, and the other one y equal m2 x plus b2. We agree that the line here represented with what? Point. So this is a point, and this is another point. Agree? How many lines can pass through this point? Can we try it? I can have one like this, which is y equal m3 . I can have another one, M4B4. If you connect all those points here in the hue space, you will find that they are forming a line. So the point in the Euclidean space represented with a line in the hue space. So they are against each other. Line here is a point here. Point here is a line here. Is this clear? Okay. So, by definition, if I have 2 points here This means that I have two lines here. This is x0, y0, and this is x1, y1. Right? Now, this intersection point between those two lines is representing what? Representing the line connected to those 2 points. So now, if I'm searching for a line here, all what I want to do is to convert every point here. Convert every point here to a line here and find the intersection in this space. This will be the line in this space. Very simple. Okay? So this is the concept of the Hughes transform. And instead of searching for the line that connects the points here, work on the line's intersection in the Hughes space, which is much easier than find the line connected all those points together. Okay? This concept is really good. So the concept of finding the line intersection instead of finding the line itself is really good. But it has one small drawback. What is it? Can you find the Hughes transform to this line? This is a line or no? It's a line in the collision space. What is the Hughes transform of this one? The general equation is y equal mx plus b. What is the value of m here?
y2 minus y1 by x2.
I'm sorry?
y2 minus y1 by x2 minus x1.
No. M here is what? The slope. What is the slope of this one? By definition, what is the slope? It's the tangent of the angle between the line and the positive direction of the x-axis, right? The angle here is what? Tan 9 equal infinity. This means that this line is a point at infinity. Go to infinity to put this point. Can you? So this representation has a problem. It can't represent all the lines in the collision space. Then how will we work? We found this concept is a really interesting concept. And it can solve our problem. But it can't represent all the lines in this case. How can we solve this? They said, instead of working with the M and B, I will convert the line and represent it using two other parameters, rho and theta. What is the rho and theta? Rho is the perpendicular distance between the origin and this point, and that line. And theta is the angle of this perpendicular distance. Did this solve the problem? Let's see. Can we describe that line now? Sorry. Can we describe that line now? This is rho, which equal 1, and theta equal 0. So yes, we can describe that line. How about the horizontal one? In this case, the rho will equal 5 and theta will equal 90 degrees. So I can now describe any line in the space. Okay? So instead of working with the slope and the y-axis cut, I will work with the radius or rho and the angle of that rho. Okay? And it can represent the same exact function of M and B. Now, assume that I have bunch of points in the space. Can I use those bunch of points to find the line? They said yes. First, what are all possible values of theta? Can start with theta equals 0 for this perpendicular line, then rotate until it arrives to the other one. Any line will lie within this area. So theta can equal 0 until 180. No other value. Right? So I will search for the value of theta within 0 to 180. And within this range, I will calculate the raw value for every single point I receive. So I will iterate over all edge points. And for each point, I'll calculate the value of the row. Then I will store the value of the theta and this row in a table. Every time I have similar value, I will increase this by 1. The point that has the number of points that have the highest edge value, all of them connected by 1 line. So if you want to see them, this visually, that's how to look like. So you see edge, 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 edge. All those represented by 1 point. All those 1 point. 1 point, 1 point. All of those points in the space. So if I have something like this, so this is edges. So this is the edge detection result. Now, if I calculate the Hue transform for this, I will find that I have 1, 2, 3, 4, 5 maximum points. If you count the number of lines here, you will find 5 lines. 1, 2, 3, 4, 5. So each one of them is a line. Okay? Now, is it always that good? So if the points in the edge look like this, straight, perfect, the maximum will be clear and I can easily find that line equation. Unfortunately, that's what I have in real life. Something like this. So in this case, I need to find the non-maximum suppression in this as well. Remember, we will always use the non-maximum suppression. So I calculate the value of H and I will search within this H to find the maximum value. Okay? Any questions? Any problems? Okay. If no questions or problems, then I think I'm done for today. And before